Welcome to June 3, 1943. The engines ran without pause. Instruments recorded continuous thrust from 01 Joule to 430. We logged temperature, pressure, and vibration readings every 10 minutes. Field log test stand 2. Engines roared against the Baltic wind, a chorus of fire and iron echoing across the dunes. The air tasted of salt fuel and fear. Deep beneath the smoke, men in gray uniforms moved like shadows, their faces lit by the feverish glow of welding sparks. They called it a research center, a harmless factory on the coast. But every sound inside was a secret. Every heartbeat a countdown. Down the concrete corridors, an engineer wiped soot from his goggles and muttered under his breath, "If this works, the world will never be the same." Above him, officers marched through rooms filled with chalk-dusted boards, each equation a weapon sharper than steel. They didn't build tanks here. They built range destruction measured in miles, not meters. At 0200 hours, the generators hummed to life. Ignition. The order cracked through the noise like a whip. The ground trembled, glass rattled, waves recoiled. From the launch pit rose a burning column, a spear of fire that clawed its way into the black sky, the first successful V2 test, though no one dared call it that yet. Miles away, Allied analysts still dismissed Peenemünde as an aircraft assembly site. To them, it was just another factory. But this place was more than steel and smoke. It was the forge of a new era of terror, the dawn of the world's first ballistic missile. The enemy never expected it. The factory was Germany's most dangerous weapon. The factory didn't begin as a weapon. It began as a dream, a gathering of young scientists obsessed with reaching beyond the clouds. In the early 1930s, long before the war reshaped their loyalties, a group of engineers met in Berlin's dusty courtyards to launch small rockets made of plumbing pipes and scrap steel. They called themselves the Verein für Raumschifffahrt, the Society for Space Travel. Their goal was exploration, not destruction. But when dreams of space met the ambitions of a war machine, those same equations were rewritten for death. By 1937, the Nazi regime had taken notice. The Army's Ordnance Office offered funding secrecy and unlimited materials. In return, the scientists would give them a weapon capable of striking London without a single German pilot crossing the channel. The location they chose was Peenemünde, a remote island off Germany's Baltic coast. It was perfect, surrounded by water shrouded in fog and far from enemy eyes. The men who arrived there called it Heeresversuchsanstalt Peenemünde, the Army Research Center. It was built from scratch with barracks, laboratories, launch pads, and underground tunnels carved through the dunes. The villagers who once fished the coastline were pushed out. A new community of secrecy replaced them, engineers, soldiers, and prisoners, all living by the same unspoken rule. No one asks what the others build. At the heart of it all was a tall, brilliant young engineer, Wernher von Braun. He had dreamed of sending rockets to the moon, but now he designed them for war. Under his direction, the team built the aggregate series A1 through A4 experimental rockets meant to test propulsion and guidance. Each failure burned more than fuel. It burned time, patience, and conscience. They measured progress in explosions. In the beginning, few believed the weapon would work. Even within the German high command, skepticism ran deep. The Wehrmacht trusted tanks and bombers, not rockets. But timing and desperation flipped the map. By 1942, Germany's war machine was stretched thin. The Luftwaffe no longer ruled the skies, and Allied bombers darkened the daylight over the Reich. The promise of a vengeance weapon, a silent strike that could reach across the sea, became too seductive to ignore. Peenemünde expanded overnight. What had once been a small coastal outpost turned into a miniature city. Railways brought in fuel parts and laborers. Prisoners from Buchenwald were transferred to construct underground tunnels where the work could continue even under bombardment. They called it Mittelwerk, the Middle Works, a place where machines lived longer than men. Inside the main assembly hall, the air smelled of hot oil and ozone. Engineers shouted in clipped technical German as cranes swung massive steel casings across the floor. The A4, soon to be renamed Vergeltungswaffe II, or Vengeance Weapon 2, took shape. It stood 14 meters tall, sleek and brutal, with fins sharp as razors. When fully fueled, it would weigh over 12 tons and fly faster than the speed of sound. No defense in the world could intercept it. Von Braun's engineers worked day and night to solve a single problem: control. A rocket moving at supersonic speed was impossible to steer by hand. They developed gyroscopic guidance systems spinning disks of precision steel that sensed motion and kept the missile on course. The mathematics were elegant, but the consequences were monstrous. The first real test came in the summer of 1942. At dawn on a windless morning, the team assembled at Test Stand 7. Officers, scientists, and soldiers gathered around the control bunker, faces pale under their helmets. When the ignition key turned, the roar that followed was unlike anything they had heard. Not the snarl of an engine, but the scream of a new physics. The rocket leapt skyward, vanished into the clouds, and moments later, a distant explosion rolled across the horizon. Applause filled the bunker. The A-4 had flown 190 kilometers further than any human-built object in history. But the celebration masked a darker truth. Every success at Peenemünde demanded bodies, thousands of forced laborers who dug tunnels, poured concrete, and assembled parts under brutal conditions. They lived on crusts of bread and feared their lives measured in shifts, not years. In the official reports, these people did not exist. Only numbers did. As 1943 began, the Allies still underestimated what was happening on that lonely island. British intelligence believed Peenemünde was building jet aircraft or radar prototypes. The code name Crossbow appeared in intercepted messages, but no one could confirm what it meant. A few analysts suspected something larger, a new weapon, but their warnings were buried beneath stacks of conflicting reports. Then came the turning point. In May, reconnaissance photos taken from high-altitude Spitfires revealed something unexpected: long concrete launch ramps, massive fuel tanks, and cylindrical structures pointing toward the sky. The images didn't match any known aircraft design. The British Air Ministry began to whisper the phrase rocket base. Back in Peenemünde, the Germans felt untouchable. Their tests grew bolder, their confidence stronger. They believed the enemy was stronger, one officer later recalled, but not faster. They thought timing and distance were on their side, that London, Moscow, or Paris could be reached before the Allies even knew what had left the ground. Every week, new shipments of liquid oxygen and ethanol arrived. Every day, the launch teams rehearsed. Even the civilians nearby could hear the earth rumble at night, though none dared ask why. Letters home were censored. Diaries were burned. The only records that survived were the logs, dry, mechanical, emotionless. Pressure nominal. Guidance stable. Impact confirmed. In those numbers hid a terrifying symmetry. The closer the Third Reich came to collapse, the closer Peenemünde came to success. When Allied analysts finally pieced together the truth, it was already too late. The factory was not a production plant. It was a launch cradle for a new age, an age where distance no longer guaranteed safety. The men of Peenemünde had turned a scientist's curiosity into a nation's revenge. And the war, though still fought by men on fields and seas, was about to cross into the stratosphere, where no soldier could follow, and no conscience could return unchanged. The enemy never expected it. The factory was not just Germany's most dangerous weapon, it was the birthplace of the future. Peenemünde's work was not only theoretical, it was brutally practical. Turning a laboratory concept into a deliverable weapon required a relentless cycle of training, failure analysis, and repetition. The rocket teams organized themselves like a small army of technicians, launch crews, fueling teams, guidance specialists, structural assemblers, and instrument engineers. Each crew learned a narrow, exacting trade, and the entire system depended on those trades being performed correctly in sequence every time. Early tests taught a harsh lesson: rockets punish improv. On the test stands an assembly error. A bad weld or a misread instrument did not merely ruin a trial, it destroyed months of work and sometimes killed crewmen. Loss rates were painfully high in the experimental phase. In the first intensive campaign of trials, the program suffered a failure/loss rate approaching 40% for test flights, meaning roughly 4 out of 10 test launches failed to reach meaningful flight goals. That figure translated into lost hardware, lost time, and a continuous pressure to refine procedures. From those failures came discipline. Peenemünde codified procedures into rigid checklists. Instrument readings had to be logged at precise intervals. Bolts received torque signatures recorded on paper. Fuel lines were leak-checked in prescribed sequences. The launch countdown became choreography. One team checked structural alignment, another verified propellant flow, a third armed guidance systems, and a fourth stood ready to abort. Each action was called out and confirmed aloud. The checklist culture didn't start as ideology, it evolved because it saved lives and preserved irreplaceable hardware. Training was both classroom and apprenticeship. Young engineers studied equations until they could recite guidance algorithms by memory. They practiced gyroscope calibration until their hands moved as if the instruments were extensions of themselves. But the classroom alone was not enough. The chief instructors demanded hands-on repetition under stress. Crews trained with inert prototypes, then with partially fueled rockets, then when confidence allowed with full static firings. This graduated exposure built muscle memory and, crucially, interperson trust. Trust was the invisible glue. At the launch pad, the crew had to trust one another absolutely. The man who handled the looser on a fuel valve trusted the man who read pressure gauges. The guidance technician trusted the mechanic who mounted gyros. The officer issuing ignite trusted the voice that reported all green. In the context of Peenemünde, trust often formed in two stages. First came procedural trust, faith that the other would follow the checklist. Second came relational trust, faith born of repeated successful operations and shared hardship. Where trust failed, operations broke down. Where trust was strong, teams could execute complex sequences rapidly and safely. The program's production tempo also shaped training. As the project matured and wartime demands grew, assembly and launch cadence increased. In mid-phase production, Peenemünde and associated facilities aimed for a throughput that would overwhelm defenses' assembly lines and final test bays combined to average roughly 0.5 to 1.0 finished unit per day at peak concentrated effort in the best organized cells translated across the entire complex and satellite sites. This meant several units per week with surges during prioritized periods. That cadence forced training to be efficient. New technicians were paired with veterans. Simulation tables used mock failures repeatedly until crews recognized fault signatures instantly. Fuel handling was another training crucible. The rockets used highly volatile propellants, and cryogenics handling ethanol and liquid oxygen demanded exact timing and respect for temperature, pressure, and contamination. Fueling sequences were treated like rituals. A single stray speck of rust or an improperly seated valve could cause catastrophic combustion anomalies. To minimize such risks, teams mapped every fuel coupling and practiced emergency venting procedures until they could perform them reflexively. Typical fuel loads for an early operational flight could be measured in the low thousands of gallons. An individual launch might require on the order of 2,000 to 500 gallons of combined propellant components, distributed between oxidizer and alcohol kerosene mixtures loaded and monitored under strict safety windows. Those volumes and the cryogenic temperatures magnified the consequences of error and thus hardened the training regimen. Failures were not merely disasters to be mourned. They were data. Peenemünde instituted post-failure autopsies with a rigor rivaling any academic lab. Fragment recovery teams scoured impact zones. Metallurgists examined casings under microscopes. Telemetry, when it survived, was parsed line by line. Each anomaly fed back into revised schematics, new tooling, or altered assembly instruction. For example, repeated guidance deviations led engineers to redesign actuator linkages and to institute tighter tolerances in gyroscope manufacture. Recurrent combustion instabilities drove changes in injector plate geometry and fuel mixture ratios. This attentive loop of fail, analyze, fix, retrain reduced the failure rate over time and hardened the crew's competence. Discipline extended beyond technique into behavioral expectations. The commanders enforced punctuality, clean logbooks, and unambiguous reporting. A late entry, an omitted signature, or a fuzzy reading was treated as a potential fault line. Punishments varied from extra drills to reassignment, but the security that procedures demanded became internalized. Operators learned not to skimp on steps even when under pressure. That cultural discipline, combined with the technical training, produced teams who could operate under the stress of air raids or rushed schedules without cutting corners. Crew cohesion was tested by secrecy. Personnel lived, worked, and died under a veil of compartmentalization. Many technicians never knew the full scope of the weapon. They performed one task and left the rest to others. Paradoxically, that compartmentalization both undermined and strengthened trust. It insulated failures from cascading across units, but it also required interpersonal bonds to bridge the silos. Mess halls, late-night tool fixes, and shared danger forged those bonds. Technicians who had braved static fires together learned each other's limits and warning signs. Those informal lessons, the whispered, "If you see that, stop," everything often mattered as much as the formal checklists. Speed and range were constantly in engineers' minds because they defined the weapon's strategic value. Operational metrics, speed to launch, flight speed, and effective range were targets around which training and expected performance revolved. Early operational profiles aimed for ranges in the 250 to 320 km band and supersonic terminal velocities. Meeting those targets required precise mass budgeting, propellant management, and aerodynamic stability. Training sequences therefore included rapid mass trim procedures, ballast loading practice, and timing rehearsals designed to get a rocket from assembly to launch pad in the smallest safe window. Finally, psychological preparation was integral. The teams had to accept moral dissonance that their elegant mathematics and mechanical skill now served a weaponized aim. The senior engineers compartmentalized by framing objectives in technical terms, solve guidance rather than strike a city, which eased cognitive strain and kept technical focus sharp. For enlisted crews and laborers, the daily grind left little room for philosophy. Surviving the shift and keeping the checklist clean was moral enough. In sum, Peenemunde's training and preparation were a crucible of rigor forged by failure. Loss rates in the early test program pushed procedures toward checklist discipline. Assembly and launch cadences demanded efficient apprenticeship-style training. Fuel volumes and handling complexities required ritualized safety and repeated practice. And the post-failure forensic loop ensured that every mistake became an instruction. Together, these elements built not only a weapon, but a machine of men, disciplined, interdependent, technically fluent, and above all trained to reduce the impossible uncertainty of rocketry into a repeatable act. Combat phase did not begin with fanfare, so much as an acceptance of a new mechanical inevitability. The rocket moved from test ranges into the logistics of killing. The factory had given birth to a projectile. The field now had to learn how to hide it, move it, fuel it, aim it, and when required, pay for it with men and rails. This phase is best understood not as a single battle, but as a concatenation of contacts across terrain, a series of radioed transactions and a cascading set of outcomes, where a handful of numbers translated into strategic tilt. Contact came in three modalities: the physical contact between launcher and ground site setup, convoy, arrival, assembly, the acoustic/kinetic contact of the missile with the target impact, and the informational contact reconnaissance and radio that bridged the two. Each modality had its own tempo, friction, and failure modes. Sites were chosen with pragmatic cunning. Fixed ramps and reinforced pads in hidden quarries offered permanence but made attractive targets for Allied air reconnaissance. Mobile erectors and rail launch conversions offered camouflage at the price of logistical complexity. Rolling farmland provided concealment by context. A train that looked ordinary on daylight inspection could by night become the cradle for a 14-meter weapon. Marshes and forests masked pipework and fuel bladders. Abandoned industrial yards provided sheds for assembly. Yet terrain is never neutral. Low-lying coastal flats favored concealment of LOX storage by distance, but they complicated drainage and exacerbated frost risk for cryogenics. Limestone quarries protected against overhead observation, but funneled access routes, choke points that could be severed by a well-placed bombing run. The first contacts in combat were hurried, noisy, and inefficient. Logistical trains slowed to move sections of missile cranes and fuel tanks. Workers offloaded parts under blackout. A typical forward assembly cell working with urgency and secrecy might assemble and prepare one finished rocket every 24-48 hours in an ideal surge and intense tempo that required disciplined crews, fuel trains arriving on time, and an unbroken chain of security. When that chain broke by an airstrike, a partisan raid, or a delayed convoy, the time to launch could balloon to 48 to 72 hours, turning a planned barrage into a trickle. Radio calls were the connective tissue of this brittle organism. The launch sequence, when under combat conditions, became a litany of confirmations over clipped VHF and wired field telephony voices that alternated between technical coolness and near prayer. A canonical exchange from a mobile node reads like the machinery of war speaking. Control status request. Mobile node. Charlie assembly complete. Guidance cage mounted. LOX temp stable at. Fuel manifold press at 28 bar. Confirm warhead arm sequence. Safety pin removed at 0210. Remote arm verified. All safeties in test position. Range set to 310 km. Wind correction plus 1.5 degrees. Sync to GMT 2145. Copy. T-30 and hold. Hold lifted. Ignition on my mark. Mark. A dull metallic intake, then a high pitch from telemetry. Ignition. Visual lift. Climb nominal. Telemetry sustained. That exchange is technical, spare, and bureaucratic numbers. First, rhetoric, last. Under the calmness lies a braided risk, one misread pressure gauge, one misindexed gyroscopic trim, and the arc would deviate into disaster. The radio network also carried different content logistic updates, damage reports, and intercepted chatter. Allied listening posts learned to monitor the cadence of such transmissions, using them to triangulate activity. Jamming and emission control became immediate counters. A launch cell that transmitted too much risked location. A launch that transmitted too little ran the risk of internal error. Terrain shaped outcomes in two critical ways: concealment/survivability of the launch complex and the ballistic environment between launch and target. Coastal launch sites exploited the sea as a buffer. The long arc over water minimized chance of early detection by area observers. Inland mobile nodes used forests and agriculture as camouflage, but their supply lines were more vulnerable. Wind layers, temperature inversions, and the vague, chaotic behavior of the lower atmosphere influenced terminal impact points, a reality that made the weapon powerful in terror, but imperfect in precision. Early guidance systems delivered a circular probable error, measured not in meters but in the hundreds of meters. Ballistic correction could not account for every eddy of wind on a particular night. The first major pattern of contact produced an outcome swing that was immediately measurable. In concentrated surges, a concentrated week of launches aimed at port and rail infrastructure. Allied logistic throughput at a target node fell noticeably. In one described instance, a surge of strikes reduced dock handling capacity at a major port by an estimated 8 to 12% over several weeks, as key cranes, warehouses, and rails were put out of service or forcibly rerouted. That percentage is deceptively small until placed in context. A single port's throughput reduction rippled across supply chains, forcing convoy delays, shifting prioritized shipments, and occasionally starving a forward echelon of timely munitions. Contact was not only physical, it was informational. Allied reconnaissance, when upgraded by photo analysis, began to recognize patterns: the arrival of refrigerated tankers for LOX, the assembly of idiosyncratic rails, the curious geometry of spoil piles around concealed pads. These informational contacts prompted immediate radio and bomber responses: the interdiction of supply nodes, the disruption of trains, the destruction of temporary depots. The logistics of the offensive proved its Achilles heel. Steel and gyros could be replaced in factories. A moving fuel train destroyed by a night raid removed several potential launches from the map. Combat Phase 1 therefore turned into a contest of tempos, launch cadence versus interdiction rate, where German forces could average surges of 0.5-1.0 finished units per day across dispersed nodes during peak periods. Allied interdictions sought to reduce that cadence below a threshold where psychological effect weakened. Each interdicted supply train or demolished crane cut not only a launch but the morale calculus that made the weapon politically consequential. Attrition of production rate, both through physical destruction and dislocation of skilled labor, proved as decisive as battlefield effects. Radio traffic provides a human counterpoint to mechanical metrics. A radio log preserved from a defense command after an impact illustrates the defensive cadence. City Watch report: explosion at 2153 Sector C3. Estimated impact radius 150 meters. Civil def to command, casualties unknown. Fire crews to Sector C3. Request heavy cranes for debris removal. Command divert engineering team. 4. Priority restore rail capacity within 72 hours. If not, shift to east intake. Copy. ETA 54 hours for materials. These mundane orders: restore crane operations in 72 hours, are the arithmetic of resilience. They reveal how a single physical impact translated into administrative cycles: hours, days, that cumulatively altered operational readiness. The swings in outcome were not purely infrastructural. Psychological effects were hard to measure, but real workforce absenteeism rose in the immediate aftermath of concentrated strikes. Factory output dipped by a few percentage points in critical windows, where an 8 to 12% hit to throughput translated into measurable delivery delays. An accompanying 3 to 5% drop in labor attendance could magnify material deficits into production pauses that lasted weeks. In a wartime economy, such multiplicative effects can matter more than single decisive blows. Yet, Combat Phase 1 also revealed the weapon's bluntness. Accuracy deficits meant that many rockets fell in open fields or industrial lots, misses that saved lives but wasted ordnance. Conversely, imperfect guidance occasionally produced politically catastrophic outcomes when strikes hit densely populated civilian quarters. Each errant trajectory complicated strategic narratives. Commanders measured both success and liability. A strike that disrupted a rail hub was strategically advantageous. A stray impact that killed civilians in a non-combatant neighborhood could shift diplomatic and domestic opinion. The balance between military effect and political cost weighed heavily in command councils. Tactical countermeasures evolved quickly. Civil defense organizations moved beyond mass sheltering. They broke critical cargo into smaller consignments, rerouted to secondary ports, and implemented rolling repair doctrines to restore damage within 48 to 72 hours where possible. Engineers built temporary shed-works to reroute cranes and improvised floating platforms to offload essential supplies. Military logistics learned to accept higher transit complexity in exchange for resilience. These countermeasures reduced the long-term swing from initial sharp drops to more modest sustained disruptions. On the German side, tactics adapted too. Launch protocols diversified. Mobile units increased dispersion and used decoys. Launch trains traveled under false manifests. False ramps soaked reconnaissance resources. Speed of assembly and mask and move techniques improved. But logistics constrained all mobility cryogenics, and volatile fuels are unforgiving. Typical fuel logistics for an operational sortie required thousands of gallons staged and matched with precise timing. A single delayed tanker or punctured bladder could cancel a planned wave. The fragility of fuel lines meant operational sustainability hinged on a complex system of supply, a system the Allies increasingly sought to break. Combat Phase 1 ended in a grinding attrition. Initial surges had demonstrated the strategic logic. Surprise, terror, and disruption were achievable, but sustaining that effect demanded a scale of logistics and industrial resilience that wartime attrition increasingly denied. Allied interdiction coupled with adaptive civil measures shrank the weapon's operational window. A practical outcome emerges: initial phases could reduce key node throughput by 8 to 12%, but by sustained interdiction and redundancy planning, that swing could be cut roughly in half in later weeks. The numerical equivalent of turning an acute shock into a chronic burden. The ledger of Combat Phase 1 is double-edged. On one side, the rocket introduced a new modality of war: high-speed remote impact that bypassed conventional defenses and imposed immediate human and administrative costs. On the other, its operational dependence on contiguous logistics, specialized components, and stable supply corridors exposed vulnerabilities that attrition and targeting could exploit. Radio calls continued to stitch together the human systems that enabled launches. Terrain continued to offer both sanctuary and trap. Outcomes pivoted on hours and ratios: launch cadence, repair windows, throughput percentages that together compose the arithmetic of modern attrition. When history measures this phase, it does not find a single decisive victory, but a transformation war no longer unfolded only along front lines and under visible danger. It now moved unseen in arcs across space, delivered by machines whose predictability in flight contrasted with the complexity of keeping them fed and hidden. Combat Phase 1 proved both the promise and the price of that transformation. The launch window was closing. Rain beat down on the trucks, freezing as it fell, turning the muddy clearing into a mirror that reflected the dim orange of work lamps under tarps. The men were exhausted. They had been awake 31 hours straight, assembling and fueling the weapon in silence. Orders were clear: the strike must go tonight. Intelligence warned of approaching Allied scouts, but the fuel already loaded could not be stored another hour. At 03:14, the perimeter radio crackled. Movement south, access road, 2 vehicles, possible patrol. The officer in charge, Lieutenant Weber froze. He had three options: abort and risk an explosion during defueling delay, and risk discovery or launch and run. He looked at the faces around him, pale, waiting. Then he said quietly, "We launch, no delays." That 1 second of choice sealed everything. Engines hummed. The men worked like automatons. Pressure readings 32 bar. LOX temperature stable. The ignition switch cold in gloved fingers. Weber's scar itched a deep ridge across his left wrist from a fuel burn months ago. It throbbed whenever he was near ignition heat. He pressed his palm against the control board, grounding himself to something that felt real. Gyro stable. Fuel flow nominal. Guidance armed. Outside rain turned to sleet. The wind cut sideways through the tarps, carrying the hiss of liquid oxygen. A sentry shouted tracer fire flared on the ridge. Someone screamed for cover, but Weber's voice overrode it. Continue countdown. 3:19. Ignition sequence start. The roar was instantaneous, devouring sound and logic. The rocket tore free, rising on a column of light that turned the night silver. For a heartbeat, every man there looked up hypnotized. Small as the weapon they had built, vanished into cloud. Then the shockwave hit. A fragment of debris flung from the blast pit caught Weber across the face. He went down hard, clutching his cheek. A mechanic dragged him aside, but his left eye was already swelling shut, blood mixing with rain. The rocket was gone, the mission successful. But the cost had landed right where they stood. Hours later, under a makeshift tent, a corporal filled out the repair log in block letters. Repair log. Node. Charlie. 26. Feb. 1945. 05:12. Event: partial blast damage during ascent. Shrapnel impact to officer in charge. 2 ground crew injured burns. 1 fuel bladder destroyed. Action site evacuated. Perimeter secured. Equipment loss 1X mobile pump. Remarks: launch successful. Impact confirmed at 0549 London sector. Signed Tech Sergeant A. Brenner. The words were clean, neutral, bloodless. They hid the smell of scorched canvas, the silence of men watching a comrade's hands shake as he tried to write his name. By noon, the camp was gone, packed into trucks moving east before Allied air could find them. Weber lay in the back of a lorry, his head wrapped in gauze. His good hand gripped a folded scrap of paper he had written hours before the launch intended for his wife in Dresden. If this reaches you, the work continues. Tell Lotta her father's hands are steady again. Tell her I will come home when there is no more sky left to burn. The letter never left his pocket. That night, on the opposite side of the channel, the missile landed. Witnesses in the city below felt it before they heard it, a tremor through the feet, and then the sound like thunder compressed into glass. The same phrase appeared again, in diaries, in after-action reports, in repair logs. You felt it in your feet before you saw it. The motif returned, the vibration, the scar, the log echoing between maker and victim. The rocket left no trace of its path, only consequences written in flesh and paper. For Weber, the scar on his face would heal white and hard. For the crew, the log would enter archives filed under operational success. For the city, there would be another hole in the street, another morning without answers. The factory's perfect weapon had achieved its aim: distance, destruction, silence. But inside that silence lived the cost: 1 scar, 1 letter, 1 line in a report that no one would ever read aloud. When the smoke settled, the arithmetic of war returned, the counting of what was lost, what was learned, and what could no longer be repaired. Peenemunde's engineers logged the numbers with precision. 358 missiles launched. Roughly half reached their targets. Hundreds fell short or failed mid-flight. On the ground, Allied reports tallied damage and deaths in similar columns. 200 to 700 killed, thousands injured, and miles of streets rebuilt twice over. The numbers matched imperfectly, but the meaning aligned. Victory and failure had blurred into statistics. Crews that survived the campaign returned to dismantled sites. They repaired what could be saved: gyroscopes, rails, burnt wiring, not for triumph, but to keep busy while the Reich around them crumbled. Some believed their skill had carried them through. Others knew it was luck disguised as discipline. In the end, there was no heroism in precision, only endurance. Leadership lessons arrived late and quietly. Officers learned that control was never absolute, Not over weather, not over fuel, not over men. Commanders who once measured worth in output began to measure it in survival. A leader's task, one wrote, is not to finish the weapon, but to outlive the consequence of building it. Across the Channel, repair crews in London wrote their own log entries: bridges, patched rails, restored, buses, rerouted. Their discipline mirrored that of the enemy they had never seen. Both sides had built and rebuilt against the clock, proving that survival itself had become an industry. By April, the rockets stopped. What remained were fragments of metal and fragments of conscience pieces that would be gathered, studied, and eventually reassembled into something meant for space, not war. In hindsight, the factory had built more than a weapon. It had built the blueprint for the modern age, the idea that distance could no longer guarantee safety, that technology could outlive its masters, and that war's truest legacy was not destruction, but acceleration. One line remained the thesis resolved. It mattered beyond the battlefield because it marked the moment humanity learned how to reach the heavens and chose first to aim for each other. After the war, the weapon that had terrorized cities became the foundation for a new doctrine. Engineers from Peenemünde were split between Victor's Operation Paperclip and the West Soviet intelligence teams in the East. The same men who once drew blueprints for vengeance now drew flight paths to orbit. The line between missile and spacecraft blurred. Propulsion became prophecy. Military planners absorbed the lesson. Technology decides tempo. The V2 taught that distance is no defense, that the next war would begin before the last one could end. Ballistic missiles became deterrence, not delivery, a paradox born from the factory's first fire. Every rocket since Atlas R7 Saturn V carries a trace of that origin, a moral residue welded into its metal. Today, Peenemünde stands quiet. Its concrete pads crumble under moss, but its legacy powers satellites, space stations, and ICBMs alike. The story is neither celebration nor condemnation. It is a record of how innovation and destruction often share the same workshop. Understanding it matters now because the same equation still governs our century: knowledge without restraint becomes destiny without conscience. The archive, not the myth, tells that truth. Subscribe for more archival-based stories where every fact is sourced, every silence documented, and evidence speaks louder than sensationalism.